morning everyone. Myself Dr. Deepak Yadav, and today we will going to discuss a very specific topic of digital system design subject, that is we are studying in semester 3, that is a combinational circuit, and in which in this series we already discuss about adders, and now this time we are going to use the topic, that is we are going to discuss the topic subtractors in digital system design. So So as we study how the combinational circuit are being designed in the digital system design subject, so that is a quick review. That is, first we are going to decide the number of the input variables and the corresponding output variable that is needed for a particular system or particular circuit designs. Like in case of our subtractor, we need at least 2 bit that we are going to use as an input, so that 1 bit is going to be subtract from the another bit, and it is going to produce a result that is either the difference of the number, or if there is any borrow that is need to be used in the subtraction process. So first of all, the design are going like this. First of all, we have to use the number of the bits required, which are going to subtract one digit from the another digit. That is, two variable is input variable is x and y, and there is the output, which is again the two variable, that is the either difference or the borrow bit. So now if we are going to design a half subtractor, so in the case of half subtractor circuit, like we have to subtract a from b, so we need at least one variable a and another variable b, and the difference is equal to the subtraction of this number, that is equal to d, and maybe there is a requirement of borrow if the a is small. Then in case of we have an output, that is borrow out for the subtraction. So the input variable is a and b, or we can say x and y over here, that is the input variables, and the output variable is d and b naught. Now for all the possible values of input variable, that is the possible values for the input variable is if x may be 0 and the y may be 0. The another possibility is x may be 0, y may be 1. The another possibility is x1, y0, and the another one is y1 and x1. So only these 4 possible combination is exist actually when we are going to subtract a single bit number from another single bit number. And the possible output of this subtraction is when x is equal to 0 is subtracted from y is equal to 0, we have the difference be 0, and there is an output, there is no borrow required, so the borrow is again 0. When we subtract y1 from x is equal to 0, then we need a borrow that is required to subtract a smaller number, subtract a larger number from the smaller number. So there is a borrow bit, that is set is equal to 1, and the difference is there when we going to borrow, that the borrow is equal to the base of the number system. So here we are going to use binary number system, so the base is 2. So now 2 minus 1, that is equal to 1. In this case, when x is high and y is low, that is the direct subtraction is possible. 1 minus 0, that is equal to 1, and there is no borrow. And in the last case, 1 minus 1 is equal to 0, and there is no requirement of borrow, then again the borrow is 0 over here. So so if we make the function for this d, then the d is having the value 1 is at the point over here x bar y, and over here x by bar, then x y bar. So the combination of d, that is difference for a half adder, is equal to x bar y plus x y bar, and d is equal to x XOR y over here. Similarly, for the borrow, this one, we have x bar y. This is not 1. This must be 0. So the output is x bar into y. So if we implement this circuit, we have the input variable x and y, and we have a XOR for the difference. So for the difference, we have a x XOR y, which is generated over here, and there is an output term as a borrow out x bar y. So this is x, this became x bar over here, and this is y. So the output is x bar y over here. So the two outputs, difference and borrow, is implemented by this circuit. We can also represent this circuit in the form of a box, as this is an half subtractor circuit, and this half subtractor is nothing but this XOR gate, this NOT gate, and this AND gate. We have two input x and y, and the corresponding output difference and borrow over here. So now if we have the circuit that are able to subtract two number, that is x from that is y from x, then we have the borrow and carry. Now we are able to subtract any amount of number from one number minus second number by the use of multiple half adder circuits. So for the binary arithmetic, binary subtraction is possible in this manner. Like we have a number x, this is represented by 229 as a decimal number, and y is equal to 46 as a decimal number. So now we can write this number into corresponding its binary equivalent over here, and for the 46 we have the binary equivalent over here. Now if we perform the direct subtraction, so always the initial borrow is 0, and we have to subtract 1 minus 0, that is equal to 1 over here. 0, this is again 0, 0 minus 1. Now this is not possible, then we have to bring a borrow over here, so this borrow bit became 1 over here. Similar subtraction is done over here. Then from 1 minus 1, that due to this borrow, this is equal to 2, 2 minus 1 is equal to 1 over here. So in this way, the complete subtraction is possible. Whatever the number of bit, we need a particular half adder for one line subtraction or one column subtraction. So with the use of multiple half adder circuit, we are easily perform this subtraction, this binary subtraction. So for doing this, we again need a full adder circuit. Now full subtractor circuit. Now full subtractor is nothing but if we want to subtract a multiple number, like we have the subtraction x minus y, but in the result we let the result be difference. Now if we want to subtract again another number z from this difference, then we need a 3-bit complete subtraction. So now in this case, we have 3 input value for the full subtractor circuit, x, y, and b in, and the output is again either the difference or it may create a borrow output, which is coming from the nearest bit. So the possible combination, all the possible combination for the input sequence x, y, and b in is equal to from 0, 0, 0 to 1, 1, 1. This is the all possible combination of the input variable. Now we have to perform the subtraction one by one, and we have to create this relationship table, or we can say the truth table. X minus y, that is equal to 0. The result is 0. From 0 result minus this 0, then again the difference is 0. So the actual difference is 0 and there is no need of borrow. In this case, x minus y, that is equal to 0. Now 0 minus 1, then we need a borrow from here. So this borrow bit is set to 1, and from 0 minus 1, that is coming from borrow side. So we have the 2, that is the base of the system. Then 2 minus 1, that is equal to 1 over here. Similarly, these processes perform for this bit again. 0 minus 1, there is a need of borrow, as well as 2 minus 1 is equal to 1, then 1 minus 1 is equal to 0. So the final result is 1 plus 0 is equal to 1 only. So in this way, the complete table is performed one by one, and we have to generate this difference and borrow output for the 3-bit input number. So for this is the truth table or relationship table of the full subtractor circuit. Now the difference and the borrow is represented as it is the sum of the all possible ones in the difference line, that is over here, and this one and this one. So we have 1, 2, 4, and 7, and for the borrow out it is equal to 2, it is equal to 1, 2, 3 and 7 over here. So we have the output for the output variable D and B out in the combination of 1, 2, 4 and 7 and 1, 2, 3 and 7. Now with the help of basic K-map, we are able to make the difference and borrow combination as well. Let's suppose we have to solve for D. So we have the input for 3 variable input K-map like this. We have a variable X over here, Y and B in 0, 1, 0, 0, 0, 1, 1, 0 and 1, 1, and we have the input 0, 1, 2, 3. This is 3 is equal to 0, 4, there is no 5, there is no 6, and there is 1, 7 over here. So if we see in this K-map, there is no possibility of any higher group like a pair or a quad or any other higher group. We can make only the single pair group like this. So if we write the output function of this is equal to the XOR of X XOR Y XOR B in over here. Similarly, for the borrow, we have the combination like this. Now we have the difference and borrow equation in terms of input variable. We have to implement this, and we can also represent full subtractor circuit in this way in the box form as well. We have the input X and Y, and there is another input that is borrow in. It produces difference and borrow out. Now if we see the implementation of the following function with the help of using basic logic gates, the difference function is like this and the borrow function is like this, and you can see over here there is a multiple number of gates are required, like there is a OR gate over here, OR gate over here, and there is a multiple of AND gate over here. Now if we want to implement this circuit with the help of a special gate like XOR gate and XOR gate, so we can represent this different function as the combination of X XOR with Y, and the final X XOR Y is again XOR with B input. So the total output difference is equal to this. And similarly for the borrow, in the case of borrow, we cannot decrease the number of gate because there is no function that is either XOR or XNOR, or we can make a combination of a special gate. So for the in this case, the implementation of borrow out is almost similar as the previous one, as we can use the simple logic gates. So this is the circuit of full adder with the help of AND gate and XOR gate. Now if we want to subtract a n-bit number from the another n-bit number, we can use n-bit subtractor. So in the case of n-bit subtractor, there is a 3-bit subtraction over here. Like if we have the X input, we have the Y input, and we have to subtract Y from X. Maybe X is smaller than Y, so we need a borrow in also. So borrow in also. So the total subtraction is the combination of subtraction of borrow in, then X, then Y, and it produces the difference and borrow out terms. So this is for a single bit. So if we have the n number of bit, so for each bit we have this combination, and then another bit we have the another same combination, So the n bit number, we need a n number of bit to subtract one number from the another number. So for doing this, we are going to use the 2's complement method. So in case of 2's complement method, we use the addition property of the subtraction by using the 2's complement method. So in this case, let's suppose the first number is X and we want to subtract Y from the X. So first of all, we take the first complement of Y, and then by adding 1, we take the second complement of Y, and when we add X in y, second complement of y, 2's complement, we have to produce the sum and the carry. So now this time the sum is equivalent to the subtraction of x minus y, because y is in its second complement form. So if there is an carry for the second complement case, we have to add this carry in the sum and we get the output, that is the difference of x minus y. But if there is no carry, then the result is in complemented form. Then again we have to perform the second complement of the result so that we can get the actual result. So this is written over here. The original subtraction is x minus y, now became as in the addition of x to the 2's complement of y using the n-bit adder circuit. Now we can see this is a binary subtractor that is going to be used, which is actually the adder circuit that we already studied in the adder video, where we use full adder to add two-bit numbers. And now we are use this same technology to subtract the two numbers by using the method second complement. So in this case, a minus b is nothing but a plus of minus b, and minus b is nothing but the second complement of the number b itself. So how we can generate the second complement? So the second complement is nothing but, let's suppose if b is equal to 1, then the second complement of b is the first complement is b's first complement is equal to 0, that is flip of the number, and the b's second complement is this 0 plus 1, that is equal to 1 again. So the second complement of b is equal to the first of all we have to perform the not operation over the whatever the bit is over here, and then we have to add binary 1. So for adding the binary 1, we can use the carry in bit. This is the initial carry in bit. That in the case of adder we always put it at 0, but now in this case we put this C0 is equal to 1, so that this extra number of 1 is added in the results for generating the second complement. So while in the second case we have to generate the flip of this bit, that is the not of the primary bit. So for that we can use the NOT gate over the B input, B0, B1, B2 and B3, and we are going to use the NOT gate over here. So now the first number is A0 alone. Now the second number is B0 bar. So this is the first complement of B0. And for generating the second complement, we have to add input that is equal to 1 in the input that is equal to 1, so that the second complement is generated. Now this full adder circuit, now this 4-bit parallel adder circuit, which is nothing but IC 7483, is going to perform the second complement. How? Because we have the NOT gate over here which can able to generate the first complement, and we have the carry in is equal to 1 that that can generate the second complement, and the addition of the number with this second complement actually perform the a minus b operation. Now again we can see this here is this 7483 IC, and again we have to use a combination of X or IC over here, which can be used this adder this subtractor circuit as a adder as well as subtractor. So this is nothing but the adder subtractor circuit, in which we have a mode number m is equal to something. If m is equal to 0, if this mode number m is equal to 0, it can perform the addition of the 2-bit number. And if we have m is equal to 1, then it can perform the subtraction by using the second complement method. And how is this possible? The property of XOR gate is nothing but, let's suppose this is XOR gate and we have the input A and B and the output of XOR Y. If it is 0, 0, 0, 1, 1, 0 and 1, 1, we have the output 0, 1, 1, 0. So if we see, if A is equal to 0, if A, one of the input of the XOR gate is equal to 0, the output is nothing but the second input bit. So if B is equal to 0, output is equal to 0. If B is equal to 1, output is equal to 1, with the condition if A is equal to 0. And if the one of the input of the XOR gate is equal to 1, the output is nothing but the flip of the first bit. Like if it is 0, then it became, output became 1, and this is 1, then output became 0. Now same property of the XOR gate is used to flip the number over here. If M is equal to 0, one of the input is of the XOR is 0. So this is the case. Whatever the number is coming, that is cross the gate as it is, and we have the same input bit. Like if B is equal to 1, the same is equal to 1 if M is equal to 0 over here. So in this case, the same number is going over here. For M is equal to 0, C0 is again 0, and this can perform the basic addition of the 4-bit number, two 4-bit numbers, because the same data is passing through the XOR gate. But if the another case is that if M is equal to 1, so M is equal to 1, make this C1 is equal, C0 is equal to 1, as well as this bit is equal to 1, and due to this property, this one property, the input bit is flip, which can generate the first complement of the input number. So if this is equal to 1, due to this M is equal to 1, this flip to M is equal, input is equal to 0. Now this bit is flipped. Similarly, if this is 0, this became 1. If this is 1, this became 0. If this is 1, this became 0. So, so the first complement is generated with the help of this XOR IC, and due to this 1, the second complement is generated. Now rest of the work is done by this 7483 IC, which can add the two 4-bit number, and the result is actually the subtraction of two 4-bit number, that is A minus B. So in this way, an adder subtractor work, where is a mode where M is equal to 0, it can perform addition, and M is equal to 1, it can perform the subtraction. Now there is another thing, there is a carry overflow. Carry overflow means the number of that we are going to store the result in a particular register, but if there is a carry, that means that register is going to be overflow. So for checking the carry, we use a variable V over here. So variable V, if the variable V is 0, there is no overflow, that is there is no last carry generated. But if V is equal to 1, there is a overflow. There is a overflow means that the number that we are going to be subtract or add must be greater, the result is greater than the actual size of the number. Let's suppose the size of the number is 4-bit, the result may be 5-bit or 6-bit. So this overflow can be detected, otherwise it can affect the functionality of the adder subtractor circuit. So the case is when the sign is same, that is both number are either positive or negative, it can generate the number that is having the higher magnitude compared to the previous one. So for detecting this, we can use this extra XOR gate, do the same property over here. If both is equal to 0, then V is equal to 0. If both is equal to 1, then V is equal to 1. Otherwise, any of the carries exist, there must be V is equal to 1 that perform the overflow operation. So this is the working of the adder and subtractors and all of the subtractors over here. Thank you for this lecture. Thank you.